This is a lecture for section 3.2 of our pre-calculus text. That section covers quadratic functions. All right, we should start with a definition. What is a quadratic function? Well, it's a function that can take one of these two forms identified here. The standard form is f of x equals ax squared plus bx plus c, where a, b, and c are all constants. The transformation form, or sometimes we call this the vertex form, is any equation that can be written as f of x equals a, some constant, times the quantity x minus h squared plus k. Okay, when we graph a quadratic function, it's a parabola. So I've sketched a little graph here of the quadratic function from toolkit functions. F of x equals x squared, that's the most basic, or maybe the parent, you could think about it that way, quadratic function with no transformations. Okay, if we're looking at an upward facing parabola, then the parabola is the name of the graph of the quadratic function, then the vertex is going to be the low point. If we're looking at a downward facing parabola, or maybe a transformed function, this would, down here would be negative x squared, right? It's reflected across the vertical axis. Then the vertex is going to be the maximum of that function, all right? So the vertex is always going to be the turning point of the graph of the quadratic equation, all right? It'd be located at hk if we have a quadratic function in its vertex form. There's the h, there's the k. That's going to be the x coordinate of that vertex and the y coordinate of the vertex, okay? If we have a standard form for the quadratic function, we can find the vertex fairly easily as well. We would find the x value by calculating negative b over 2a, where b is the coefficient of the x term, and a is the coefficient of the x squared term, right? Then to find the y coordinate of that point, we simply plug our x value into the function and calculate the y coordinate. All right, let's look at some examples. Let's look at some examples of finding the vertex. Here we have a couple of quadratic functions in their standard form. All right, so to find the vertex from standard form, the x coordinate of the vertex is negative b over 2a. The y coordinate of that vertex is, we're just going to plug that value into the function and calculate it. So it'd be f of negative b over 2a. All right, so that's the vertex. Let's go ahead and find it. What is a, b, and c on this function f of x? Well, there's no value in front of the x squared. That means the a is 1, right? The b, of course, is 12, and the c is 32, right? So that means that the x coordinate of the vertex, negative b over 2a, is going to be negative 12 over 2 times a, that's 1. Negative 12 divided by 2 is negative 6, right? To find the y coordinate of that vertex, we'll plug negative 6 into the function. So that'll be f of negative 6, or negative 6 squared plus 12 times negative 6 plus 32. Let's see, what is that? 30, whoops, I'm doing a graph here. Okay, let's see, negative 6 squared is 36, and then plus 12 times negative 6 plus 32. Looks like it's negative 4. The y coordinate is negative 4. So the vertex occurs at negative 6, negative 4 for f of x. All right, here's another one. I think we'll skip that. It's just not going to do anything different than it did in the first one. All right, let's look at an example of finding the equation of a quadratic function when all we have is the graph. All we have is a graph. So here's a graph. Now, if you look at that graph, I can see that that's a parabola. It's upward facing, right? So I know that that's going to be quadratic in nature. All right, the vertex on this parabola would be the local minimum, which is also the global minimum here. So it's this point right here. It looks like the coordinates of that point are -2, -3, right? Now, if we, probably the easiest way to find this equation or this formula for this quadratic function is to use the vertex form or the transformation form, which says that the function is equal to a times x minus h squared plus k, where hk is the vertex. All right, so I can just plug these two values in to that vertex form and almost have the entire formula. Let's take a look at it. F of x would be equal to a. I don't know what that is yet, right? But x minus h, what is h? Well, the h here is -2, right? So the x minus -2 quantity squared, and then plus k. K is -3, so that's plus a -3, right? Boy, isn't that awkward. Let's simplify that a little bit. A times x plus 2 squared, right? And then plus a -3, of course, is just -3. So I almost have my formula here now. I just got to figure out what that a is, don't I? Well, how am I going to find that a? Well, the easiest thing to do is to find a clear point on the graph. So a clear point, that's one where I can really see what the x and y coordinate values are. Look, these are all in between and decimals, but look at this point here. That looks like the graph is crossing right exactly at the intersection of the tick mark. So it looks like the coordinates of this point look like they are exactly 1, 0. Okay, 1, 0. So I should be able to plug that x coordinate and that y coordinate in to the equation I have so far and then solve for a. All right, so f of x is function notation for the y. So I'm going to say 0 is equal to a times, and the x coordinate is 1, so I'll say 1 plus 2 squared minus 3. I just want to solve for a then. All right, so simplifying, I would have 1 plus 2, that's 3, right? 3 squared is 9, so I would have 9a minus 3. If I add that 3 to both sides, then 3 is equal to 9a, divide by 9, and I see that a is 3/9, or that'll reduce down to 1/3. There we go. Now I have everything I need to write the equation. It's f of x equals 1/3 x plus 2 squared minus 3. Okay? All right, so what if I have a quadratic equation in standard form, but I need it to be in vertex form? Can I do that? Can I change between forms? Yes, I can, right? To change this quadratic form over to the vertex form, what I need to do is something called completing the square, right? Completing the square. So how would I do that? There's a couple of different methods or steps that you can follow. You can Google it if you'd like to see some alternatives. I think maybe there's a, a link to a video of an alternative in Blackboard as well. But let me show you how I usually do this. All right? So what I usually do is I take my equation, x squared minus 8x plus 15, and I set it equal to 0. Right? And then what I do is I move that constant term over to the other side, right? So I'll say x squared minus 8x, subtract 15 from both sides. So that's going to be equal to negative 15, all right? Then, so the first step is, if we were to write it out, move the constant to the other side of the equation, to the other side. Okay, and then the second step here is going to be to add b over 2 squared to both sides. Okay, so here's the b. What is that b over 2 squared? Right, well, that's going to be negative 8 over 2 squared. Let's just write that. So b over 2, negative 8 over 2, it's negative 4, so 4 squared. So I want to add 16 to both sides. Right, let me simplify a little bit then. Negative 15, excuse me, plus 16 is just 1, right? And then look at this, x squared minus 8x plus 16. This is a perfect square trinomial. If I were to factor this, this is going to factor into x minus 4 squared, right? X minus 4 times x minus 4, that's going to be x squared minus 8x plus 16. So if I factor that trinomial, I will get x minus 4 squared. Now, it's always going to factor into a perfect square because we've added what we've needed so that it would factor into a perfect square, right? So then I will have my equation in vertex form. All I have to do is move that constant back over. So move the constant to the other side again. And I will have the equation that I need. Right? X minus 4 squared, subtract 1 from each side, minus 1. All right, so now my equation, my equation is in vertex form. All right, it can be a little more complicated. If I have a coefficient here in front of this x squared, I have to factor that out first, right? But then otherwise it's pretty much the same process. Okay, now what if I have the vertex form and I want the standard form? Well, that's nice and easy. All I have to do is simplify the vertex form and multiply it out, right? So y would equal x minus 4 times x minus 4 minus 1, right? When I multiply x minus 4 times x minus 4, I get, let's see, x squared, negative 4x, and another negative 4x, or negative 8x, and then negative 4 times negative 4, positive 16, minus 1, right? Simplify that. Y equals x squared minus 8x plus 15, right? Of course, that's what we started with. Two forms of the same quadratic equation. All right, let's look at an application. Okay, Jamie designed a new style of sports bike and wants to sell them. Jamie found the function to model the profit earned or received from those bikes is written here. Profit as a function of C. What is C? C, I think, is the number of bikes sold. And I think that's a typo. I think that should say the number. Oh no, it's the dollars. It's the cost of the bike. All right, let's write that out because that's kind of confusing. C equals the not cost, the price of the bike. We're going to call it price. The price of the bike. Okay, C is equal to the price of the bike. All right, determine the price that Jamie should sell these bikes for to earn maximum profit, and then find what that maximum profit is. All right. Okay, so P of C, this is profit as a function of C, where C is the price that we sell the bike for. From the person buying it, it's the cost of the bike, right? All right, so what does it mean? So if this is a parabola, and it's a downward facing parabola, the maximum is going to be the vertex of that parabola, right? And look at this. If I were to graph this, it's going to be a downward facing parabola. Because look at A. It's negative, right? Remember, toolkit function, if it's positive, it's an upward facing parabola. If you reflect it, it's a downward facing parabola. So we know this is a downward facing parabola. So we know that the maximum output of this function, this profit function, is going to be the vertex of that parabola. So let's just go ahead and find the vertex. That should tell us what it is, right? Well, the x-coordinate, or in this case, the c-coordinate, is going to be negative b over 2a. Well, what's b? B is 92,000. So it's going to be negative 92,000 over 2a. A is negative 200. Right? So we want 92,000 divided by 400, or negative 92,000 divided by negative 400. Of course, those negatives will divide out, cancel each other out. And it looks like it's $230. We should sell that bike for $230. That's the selling price of that bike, or the cost the purchaser would pay for that bike to maximize profit, right? Because that's what C was. All right, what would that maximum profit be? Well, the maximum profit is going to be P of $230. So I'll plug the 230 in for the C. So negative 200 times 230 squared plus 92,000 times 230 minus, what is that number there? 8,400,000, right? Lots of zeros there. Let's see what that maximum profit is. All right, negative 200 times 230. Put that in my calculator over here. There, you see it now. Times 230 squared plus 92,000 times 230 minus 8,400,000. What do we get? Looks like it's, how many zeros? We've got 2,180,000. Is that right? 4 zeros? Yeah, 4 zeros. And then, of course, is dollars. So we would want to indicate the units there as well. Let's look at another one. There's a classic quadratic application. Quadratic applications are often used to find a maximum or a minimum, but they can be used to find other things as well. Here's one where we have a ball. It's being launched such that the height in feet of this ball above the ground after t seconds, okay, so h is height, t is amount of time in seconds, is given by this function here. H of t equals, okay, wrapped, so let me put it there. H of t equals negative 16t squared plus 48t plus 100. Well, that negative there is telling me that that's a reflected quadratic function, right? So this is going to be a downward facing parabola, like that, right? All right, so determine the initial height of the ball. So it's launching off of some launcher probably, right? I don't know what. We'll say there's some launcher. And the ball leaves that launcher at some point in time. What would the initial height of that ball be? Well, you know, once you get comfortable with quadratic equations, you'll know that it's the constant that's being added out at the end, right? Because that's a shift up or a shift down, so it's going to be 100. Another way you could find that initial height is say, well, the initial height is when time equals 0. So another way would be to find h of 0. Right? H of 0, what is that going to be? Oh, negative 16 times 0 squared plus 48 times 0 plus 100. All right. So, of course, it's the vertical shift of shifting up 100 feet. Right? Shifting up. Or the initial height can be found as h of 0 as well. It is feet. Yeah, that's my units, feet. So let me put that on there. Okay, so determine how long. Oh, that's going to be a t, right? How long. Determine how long it will take for the ball to reach its maximum height. The maximum height, well, that's up there at the vertex, right? The maximum is going to be at the vertex. How long? So we're going to find t at the vertex, right? Well, the vertex, we know that the vertex is in standard, from an equation in standard form, it's negative b over 2a, and then f of, or in this case, h of negative b over 2a. So how long, or the t, of course, is going to be the independent variable, the negative b over 2a. Let's see what that is. Negative b over 2a is going to be negative 48 over 2 times negative 16. Right, what's that? 48 divided by 32, 1.5. So it's only going to take 1.5 seconds to reach its maximum height. Okay, it starts at 100 feet. In 1.5 seconds, it reaches its maximum height. Now, what is that maximum height of the ball going to be? Well, I just need to plug that value for t into the equation to find the height at 1.5 seconds, right? So h of 1.5, right, so that's negative 16 times 1.5 squared plus 48 times 1.5 plus the 100. Now let's see what that is. Negative 16 times 2.25, or let's see, 1.5 squared plus 48 times 1.5, and then plus the 100. It's 136 feet. Makes sense? Yeah. Started at 100 feet, went up, and this should be, I don't have this drawn to scale very well, do I? But that's okay. It starts at 100 feet, it goes up here to 136 feet. And then, of course, the gravity is going to cause it to come back down to the earth. It's going to hit the earth at right here. All right, which is, what does the next question say? How long it takes the ball to hit the ground, right? Or how long it takes the ball to get down to here. How long? That's going to be a t again, right? I want to find out how much time it takes. So I'm going to find t. I want to find t down here. T down here. How do I find that? How do I find that? Well, I want to, what is the height when it's on the ground? It's 0, right? So to find when that occurs, I want to say h of t equals 0, and then I'll just solve for t, right? So let's do it. We're going to say 0 equals negative 16 t squared plus 48t plus 100. I need to solve for t. All right, let's see. I think I'm going to need to, I could just use the quadratic formula here, couldn't I? Or I could factor, 100 is not evenly divisible by 16. Factoring doesn't look like it's going to be fun. So I'm going to go ahead and use the quadratic formula. And what I've done, and what y'all are welcome to do as well, is I've programmed a quadratic formula into my calculator, right? So look, I've got this program key here, and I've already programmed these in. Actually, it's really the same thing. If you'd like to do the same, I would encourage it. Just Google it, quadratic formula solver on whatever model of calculator you have. I guarantee you'll find something there. So I'll show you what mine looks like. There it is. Display ax squared plus bx plus c equals 0. Prompt for a, b, and c. And it's going to ask me what those values are. What values do I want to use for a, b, and c? And then it's going to calculate b squared minus 4ac, stored in another variable d. Right? It's going to find the negative of that, the positive of that, and then display the answers. Right? Feel free to Google that. I've got another one that I did just because I was playing. This one looks a little different. Let's look at the edit on that one. This one's a little different. I still displayed prompted. I'm not actually. Oh, I was playing with these variables, this command del var, so I wrote a little bit different one there. Okay, so let's see. I want to use it. So I'm just going to say program. Either one works. They both work. So I'll use the first one. Enter. All right, it's asking me for my A, B, and C. Well, what's my A? Negative 16. Put that in there. What's my B? 48. What's my C? 100. And there are my two answers. T, the two solutions to that quadratic equation are negative 1.4 and positive 1.4. No, I'm sorry, positive 4.4. Said that wrong. Negative 1.4, positive 4.4. You know, we often get two solutions when we solve a quadratic equation, right? However, look at the context of this guy. Time, negative 1.4 seconds. That doesn't make sense. We've got a domain here that's restricted by the context of the application, right? If we were just doing this mathematically, there, the negative 1.4 would be there. But we launched it here. We can never go back in time. Makes no sense, right? So here's my answer. It's 4.4 seconds. Okay? Classic quadratic application there. All right, let's go one more thing. One more application, just one more. Here we have a retail manager, right? This person has found that when a certain bike is sold for $500, 45,000 bikes are sold. It's probably nationwide, right? In 1 month, during the month. Okay, 45,000 bikes in 1 month when the price is $500. The manager also noticed that if they lower the price to $440, or if they have a sale, right, the bike's on sale for $440, they sell more bikes. They sell 60,000 bikes. So, assuming that the number of bikes sold are linearly related to the price of the bike, okay, that's an interesting phrase. Let's underline it. Okay, so that means that how many they sell and the price of the bike have a linear relationship. Then find the price that would maximize monthly revenue. Well, we can't find a maximum from a linear function. We're going to need a quadratic for that, right? Okay, so I'm just sort of modeling how I solve these problems. I'm just thinking about this a little bit. What am I ultimately looking for? I'm ultimately looking for a price. All right, so I understood what I was saying here. Now I've got to think about how I go about doing that. Well, there's some linear relationship going on. Let me start there. So the number of bikes sold. Okay, so that's what's related linearly to the price. Number of bikes sold is linear related to the price of the bike. Okay, I got that. I better get some variables here involved, huh? Okay, so how about number of bikes sold? Let's let x equal that. All right, so x will be the number of bikes sold. Okay, we're going to need a price for that bike too, aren't we? We're going to need a price, P. We'll let P be the price of the bike. Okay, some variables. So these are the two things that are linearly related. So I should be able to come up with a linear function from that, shouldn't I? Well, let's see, we do have some data, don't we? But there's a price and there's a number of bikes sold. Okay, there's another price and a number of bikes sold. Okay, so let's see. I could come up with a price function here, couldn't I? Let's see if I can do it. I got two sets of inputs and outputs for a price function, right? The first set is at a price of 500. I sell 45,000 bikes. The second set is at a price of 440. I sell 60,000 bikes. So I've got an X and a P, another X and another P, like an X1, P1, X2, P2. I think I can find a way to change there, can't I? Let's use our slope formula. Instead of Y's here, we're using P's. We'll just say P2 minus P1 over X2 minus X1. Well, what's that going to be? 60,000 minus 45,000. Okay, divided by X2, 440 minus 500. So is that 15,000 divided by negative 60? Let's see what that is. 15,000 divided by 440 minus 500, that's negative 60. It's going to be negative 250. All right, so what is that telling me, that number, that negative 250? Right? Well, that says, what is that telling me? That says, is that saying if I lower the price by 250, I sell one more bike? I think that's what that's saying. Or is that saying if I lower the price by $1, I sell 250 more bikes? Oh no, that's what it's saying, isn't it? Or if I raise the price by $1, I sell 250 less bikes. Okay, so there's a slope. Can I write this equation? What equation was I trying to write again? A price equation. All right, so price is going to equal, there's my rate of change, negative 250 X, number of bikes sold. Oh, and then I've got to have some B maybe, huh? Some initial value, right? Or starting point here, like a y-intercept. Let's see if I can, let me plug one of these numbers in, see what that B would be. Let me just use the first one. 45,000 equals negative 250 times 500 plus B, we'll solve for B. Well, let's see what that is. Negative 250 times 500 is negative 125,000, right? So 45,000 is negative 125,000. Okay, so add 125,000 to both sides and I'll find my B. All right, so 45,000 plus 125,000 is 170,000. Now I've got my equation done. Here's my price equation. P equals negative 250x plus 170,000. There's my price equation. Okay, all that's really cool. Now what did I do and what am I looking for? Let me come back to my problem again, right? Let's see, assuming the number of bikes are sold are linear related to the price. Okay, so I found that price function. But I need something quadratic here because I want to maximize monthly revenue. Oh, I think I need a revenue function. Well, revenue is always going to be price times the number of quantities sold. Right? So my revenue function here, I could say that revenue is a function of price, or I could say that revenue is a function of the quantity sold. I think it's going to be more valuable to say it's a function of the quantity sold. So I'm going to say revenue as a function of X, it's the number of bikes sold, is going to be P, or, look, I've got this equation for P. Let me put that in there. Negative 250X plus 170,000 times the quantity sold, one more X, right? Now, if I simplify that revenue equation, I have negative 250x squared plus 170,000x. There's the quadratic function that I was looking for here. All right, now I can find a maximum on that quadratic function, but because it's negative, so it's transformed, it's like this. Maximum is going to occur at that vertex, isn't it? Well, let's see if we can find the quantity of bikes that produce our maximum revenue, right? Or the negative B over 2A. What is that? B here is 170,000, so negative 170,000 divided by 2 times negative 250. So 170,000 divided by 500. Let's see what that is. Oh, get my zeros straight. All right. It's 340. So what is this telling me? This is X, right? It's X, so it's 340 bikes, right? So if I sell 340 bikes, that maximizes revenue. Is that right? Let's see a calculation. All right, so that's not what we're being asked. So what is that maximum monthly revenue? So we're going to need to plug that 340 in to the revenue function. So revenue is a function of 340. Let's see what it is. Let's see, that's going to be negative 250 times 340 squared plus 170,000 times 340. Let's find out what that is. Negative 250 times 340 squared plus 170,000 times 340. Some numbers and some zeros. Let's see what they are. 2, an 8, a 9, and how many zeros? 1, 2, 3, 4, 5 zeros. All right. So that's going to be $28,900,000. It's clearly what I want to do if I'm managing the sale of these bikes, isn't it? Clearly what I want to do. All right. That ends the lecture for section 3.2, quadratic functions.